Yeah, so Twist of Azure supports different types of data transfers. So for the broadcasting, we use tree-based broadcasting, and we use direct TCP memory copy to push data from the map to reduce, and also for broadcasting. But in here, we perform a hybrid data transfer, because we also upload that data back into the Azure blob storage or the table storage as well. Because since we're operating in the cloud, the networks are deterministic, and you have a lot of, you can lose data. And so when you're doing the direct TCP transfer, we just do a best effort transfer, so the data can get lost, and in such cases, the data would be persisted in the, so we have the backup mechanism where the data is persisted in the blob storage or the table storage, and then the workers can pick it from there. But in a world where everything goes right, I mean, if we can operate, I mean, if the computation operates mainly on the direct TCP transfer, I mean, this makes the computation much faster than relying on the blob storage. Yeah. Twist of Azure supports several types of fault tolerance. So the first is the iteration level fault tolerance. So if you are using iteration level fault tolerance, whenever a task fails or a node goes down, the whole iteration will be rolled back and re-executed. And then Twist of Azure also supports traditional MapReduce fault tolerance, where the re-execution of the failed task as well. And then all our data communications, where we use direct TCP communications, are backed by storage to the persistent storage as well. So if any of this data communication doesn't make it or gets any connection issues, the workers are free to fetch data from the high latency storages. And then we have the decentralized control architecture. So this is mainly there because the cloud nodes are traditionally considered much more unreliable than the traditional cluster nodes. So they are much more prone to failures. So in such scenarios, if we have a centralized controller or a master node which should coordinate the computation, if it goes down, then our whole computation will be lost. So in Twist of Azure, we operate based on a decentralized architecture, where we avoid this single point of failure. So we'll go into the collective communication. So we are working on adding collective communication primitives to the iterative MapReduce paradigm. So this would add support for common higher level communication patterns, and the advantages of this would be threefold. One is the performance benefit you get by having the framework, having the ability to optimize these computations underneath without the knowledge of the users. And then the advantage you get by avoiding the unnecessary steps of your MapReduce computation. So for example, if you can think of, one primitive we are working on is called AllGather. So in there we have seen in several of our applications where you just, whatever the output of the map task would be, the reduce task would be just a collection and then transfer into the next iteration. So in such a scenarios, we can avoid the reduce task as well as the merge task by coming up with a communication primitive where the data from the map task would be transferred to all the nodes using a one-to-all broadcast, and then would be collected together in the destination map task. So that's kind of like the advantages you can get. And the other thing is the ease of use, because now the users don't have to worry about implementing the reduce or the merge task. Yeah, so these are some results we got. So this is a Kmeans clustering computation, and then so the top left-hand diagram shows the task execution time histogram, and each of these bars represent iteration. So you can see the execution time for the first iteration is much higher than the subsequent iterations. So this shows the benefits of the data caching. And then the diagrams in the bottom shows Twist of Azure scaling, the weak scaling and the strong scaling up to 256 Azure instances. So the bottom right-hand diagram shows the Twist of Azure performance compared with Twister, the Java Twister framework, as well as the Hadoop framework. So you can see the Twist of Azure scales more or less the same as the Java Twister, which is operating in a dedicated local cluster. And then it performs much better than Hadoop running in a local cluster. So MDS is another application which has that multiple applications per iteration, but I probably wouldn't go into details because we are almost running out of time. So this shows the execution trace of the multidimensional scaling application. So similar to the above Kmeans clustering graph, the top graph shows the execution time histogram, and you can see the first iteration is much more costly in the multidimensional scaling application, and the subsequent iterations are much faster. Earlier when we started using Azure for MDS, we initially noted some tasks having abnormal execution times towards the end of our computations. So we found out this is due to an issue with the process memory usage in I think Windows operating system. So that's why we started using memory map files for caching. So when you use memory map files, the data stays outside of the address space of your computation, of your process. So that made that whatever the issue we had with this abnormal high computation time task go away. Yeah. So this is some performance with non-iterative applications like traditional MapReduce application, the pleasingly parallel applications.